September 28, 1942. The ways at Kaiser's Richmond Shipyard No. 2 in California. A hull frame designated SS Robert E. Peary sat waiting for her keel-laying ceremony. Traditional maritime protocol called this moment sacred, the placement of the first structural member, blessed by shipwrights who understood that months of careful construction lay ahead. Except Henry Kaiser had no intention of following tradition. What happened over the next 4 days and 15.5 hours would either prove that American industrial genius could rewrite the rules of shipbuilding or expose Kaiser as a dangerous charlatan gambling with sailors' lives. The stopwatch started at 10:45 in the morning when the first keel plate touched the building way. By November 4th, the Peary would slide into San Francisco Bay as a complete, operational 10,440-ton cargo vessel. 4 days. Not 4 months, not even 4 weeks, 4 days from bare steel to a ship capable of crossing the Atlantic. The newsreels celebrated it as an American miracle. President Roosevelt mentioned it in a fireside chat. The Maritime Commission issued press releases, but nobody asked the question that mattered. If you could build a Liberty ship in 4 days, why was everyone else taking 42? And more importantly, what corners were being cut to achieve speeds that violated every principle of traditional shipbuilding? The answer involved an engineer named Henry Kaiser who had never built a ship before Pearl Harbor, a construction method the Navy called illegal because it ignored centuries of maritime practice, and an assembly line philosophy borrowed from automobile factories that would transform not just shipbuilding but the entire concept of how America manufactured complex machinery during wartime. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why Kaiser's 4-day ship seemed impossible, you need to understand what shipbuilding looked like in 1941. Traditional methods hadn't changed fundamentally since the age of sail. You started with a keel, the spine of the vessel, laid along a sloped building way. Then you erected ribs, massive steel frames that defined the hull's shape. Then you attached the skin, steel plates that were individually measured, cut, heated, shaped to fit the curves, positioned by hand, drilled for rivets, and finally secured by teams of riveters who worked for weeks to connect thousands of plates with millions of individual fasteners. A competent East Coast shipyard like Bath Iron Works in Maine could complete a 10,000-ton cargo vessel in about 8 months. The process employed hundreds of skilled craftsmen, shipfitters who could read complex blueprints and translate them into 3-dimensional structures, riveters who'd spent years learning to drive fasteners at angles in confined spaces, marine engineers who understood how hulls flexed in ocean swells and where to reinforce stress points. Every ship was essentially custom-built. Even vessels constructed from identical plans required constant adjustment and hand-fitting because steel plates never came out perfectly flat, frames never aligned exactly, and the accumulated tolerances meant that by the time you reached the superstructure, nothing matched the drawings anymore. Experienced shipwrights could compensate. They'd shim a gap here, add a doubler plate there, grind down a high spot. The final product was seaworthy and strong, but it reflected hundreds of individual decisions made by craftsmen who understood their trade. Then came September 1939, and Germany invaded Poland. Britain, with the world's largest merchant fleet, suddenly found herself fighting a naval war against U-boat wolf packs that were sinking cargo vessels faster than British yards could replace them. By mid-1940, German submarines had sent over 4 million tons of Allied shipping to the bottom of the Atlantic. Britain's shipyards, many damaged by Luftwaffe bombing raids, couldn't keep pace with losses. The mathematics were brutal. British yards could produce about 1 million tons of new shipping annually. U-boats were destroying over 3 million tons per year. The gap was widening, and Britain was slowly being strangled. The United States, still officially neutral, watched these numbers with growing alarm. American strategists understood that if Britain fell, the United States would face a hostile Europe controlled by Nazi Germany with no allies and no staging ground for any potential counteroffensive. In September 1940, Roosevelt pushed through the destroyers for bases deal, trading 50 old American destroyers to Britain in exchange for naval base rights. But destroyers couldn't carry cargo. Britain needed merchant ships, hundreds of them, and she needed them immediately. The solution came from an unexpected source. The British had designed a simple, rugged cargo vessel called the Ocean class. These weren't elegant ships. They were deliberately archaic, powered by coal-fired triple-expansion steam engines, a technology that dated back to the 1890s. British designers chose this obsolete power plant precisely because it was obsolete. Modern diesel engines and steam turbines required precision manufacturing and rare alloys that were needed for warships. The old-fashioned triple-expansion engine could be built by any facility capable of casting large iron components. It was slow, inefficient, and utterly reliable. The British government approached the United States Maritime Commission in December 1940 with a proposal: license the Ocean-class design to American shipyards. Modify it slightly to use American standard components and welded construction instead of British riveting, then build them in quantity. The Commission agreed, creating what they initially called the EC-2 emergency cargo vessel. The press would call them Liberty ships, a name that stuck despite its propaganda origins. The Maritime Commission faced an immediate problem. American shipyards were already operating near capacity-building warships for the Navy's expansion program. There simply wasn't room to add hundreds of merchant vessels without either displacing naval construction or building entirely new facilities. Traditional thinking suggested this was impossible. You couldn't just create shipyards from nothing. The infrastructure took years to develop, the workforce required specialized training, and the supply chains were already stretched supporting existing yards. Henry Kaiser looked at that problem and saw opportunity instead of obstacles. Kaiser was 59 years old in 1941, a self-made industrialist who'd built his fortune on massive construction projects. He'd paved roads across Cuba, constructed levees in Mississippi, and most impressively, managed the concrete consortium that built Boulder Dam, later renamed Hoover Dam, the largest concrete structure on Earth at the time. But Kaiser had never built ships. He'd never even worked in a shipyard. When he approached the Maritime Commission in early 1941 proposing to build Liberty ships, the Commission's initial response was skeptical. Kaiser had no maritime experience, no shipbuilding facilities, and no workforce trained in naval architecture. What he did have was an understanding of mass production that most shipbuilders had never considered. Kaiser had spent 20 years building large structures under impossible deadlines in remote locations. He knew how to organize labor, manage logistics, and most critically, he understood that traditional methods only seemed inevitable because nobody had seriously questioned them. The Commission awarded Kaiser contracts for 30 Liberty ships in January 1941, conditional on him constructing yards capable of building them. Kaiser's response demonstrated why he'd become successful. He didn't build one shipyard. He built 7, clustered around the San Francisco Bay Area, Richmond yards 1 through 4 on the east side of the bay, 2 yards in nearby Oakland, a smaller facility in Sausalito across the Golden Gate. By November 1941, Kaiser employed over 90,000 workers in facilities that hadn't existed 12 months earlier. The scale was unprecedented, but scale wasn't Kaiser's real innovation. His revolution came from asking a question that traditional shipbuilders considered heresy. What if we stopped building ships like ships and started building them like cars? The automobile industry had spent 30 years perfecting assembly line production. Henry Ford's River Rouge plant could take raw iron ore delivered by Great Lakes freighters and output a complete Model A automobile in 41 hours. The steel went through blast furnaces, rolling mills, stamping presses, and assembly lines in continuous flow with minimal human intervention at each stage. Kaiser studied Ford's methods and asked why the same principles couldn't apply to ships. Traditional shipbuilders had a list of reasons. Ships were too large for assembly lines. Every vessel had unique characteristics requiring custom work. Marine construction required skills that couldn't be simplified. Saltwater service demanded quality that mass production would compromise. Kaiser dismissed every objection. Ships were large, but they were also hollow structures that could be broken into smaller sections. Unique characteristics were mostly myth. 90% of any Liberty ship was identical to every other Liberty ship. Skills could be simplified through better organization and specialized tooling, and quality didn't come from slow craftsmanship, it came from systematic process control. His first radical decision was welding instead of riveting. This wasn't actually Kaiser's innovation. The British had already specified welded construction for ocean-class vessels because welding was faster than riveting and produced lighter structures. But Kaiser took welding to extremes that alarmed maritime traditionalists. A riveted ship had natural boundaries. Each plate was a discrete element connected to adjacent plates by mechanical fasteners. If you needed to modify something, you drilled out some rivets and replaced a plate. Welded ships were continuous structures where every plate fused directly to its neighbors. This made them lighter and faster to construct, but it also meant that stresses and failures could propagate through the entire hull in ways that riveted construction prevented. The Navy's Bureau of Ships opposed large-scale welded construction. Their engineers argued that welding created residual stresses in steel, that American shipyards lacked sufficient welders to build hundreds of vessels, and that quality control would be impossible with thousands of semi-trained workers running torches. The Maritime Commission overruled them. The war situation was too desperate for conservative approaches. Kaiser's second innovation was prefabrication. Traditional shipbuilding assembled vessels on the building ways, the sloped platforms where keels were laid and hulls took shape. Every plate, every frame, every piece of structure was brought to the ways and fitted in place. This meant the building way was occupied for months, while workers swarmed over the growing hull. Kaiser proposed the opposite approach. Build major sections of the ship in covered fabrication shops away from the building ways, then transport these massive assemblies to the ways for final joining. The concept was simple. The execution was unprecedented. Kaiser divided each Liberty ship into roughly 150 separate sub-assemblies, a bow section weighing 70 tons, side shell sections of similar weight, deck assemblies that covered thousands of square feet, engine room modules containing machinery, piping, and electrical systems already installed and tested. These prefabricated sections were built simultaneously in different parts of the shipyard. While welders assembled the bow in fabrication shop A, other teams built the stern in shop B, the midship sections in shop C, and the superstructure in shop D. Each fabrication shop contained specialized jigs, metal frameworks that held components in precise position. Unlike traditional ship fitting where workers eyeballed measurements and hand-fitted pieces, jigs guaranteed that every bow section built at Richmond was identical within a 1/16 of an inch. This interchangeability meant that any bow could fit any hull, any superstructure could mount on any deck. Parts became truly standardized in a way that custom shipbuilding had never achieved. The prefabrication shops operated around the clock in 3 8-hour shifts. Kaiser paid premium wages, attracting workers from across the country who flooded into the Bay Area looking for high-paying war work. Most had never seen a shipyard before. Many were women who'd been housewives 6 months earlier. Some were teenagers, barely out of high school. Almost none had the years of training that traditional maritime trade unions required. Kaiser didn't care about credentials. He cared about whether someone could learn a specific task and repeat it accurately. His training program broke down traditional ship-fitting skills into hundreds of discrete operations, so simple that new workers could master them in days rather than years. A traditional shipfitter needed to understand hull geometry, stress distribution, and complex spatial relationships. Kaiser's workers needed to know how to position a template, tack weld a joint in sequence, and verify dimensions with a gauge. The jigs did the thinking. The workers did the welding. By summer 1942, Kaiser's yards were producing Liberty ships in an average of 42 days from keel laying to launch. This was already revolutionary. East Coast shipyards were averaging 5 to 6 months for similar vessels. But Kaiser knew 42 days wasn't fast enough. The Battle of the Atlantic was intensifying. German U-boats were operating in wolf packs, overwhelming convoy defenses, and sending dozens of ships to the bottom every month. British import tonnage had dropped below sustenance levels. If the trend continued, Britain would be starved into surrender before America could mobilize fully. The Maritime Commission needed more ships faster. Kaiser promised he could deliver. The Robert E. Peary project in September 1942 was his proof of concept. Everything that Kaiser had learned in 9 months of Liberty ship production came together in one carefully orchestrated demonstration. The Peary wouldn't just be fast. She would shatter every assumption about how quickly a complex machine could be manufactured. The preparation began weeks before the ceremonial keel laying. Kaiser's production planners mapped every operation down to individual welds. They identified the critical path, the sequence of tasks that determined minimum construction time. Everything else would be parallelized, executed simultaneously by teams working on different sections. The goal was to minimize the time that any worker or machine spent idle waiting for previous operations to complete. Richmond Yard 2 was reorganized specifically for the Peary. 6 fabrication shops worked on pre-assembled sections weeks in advance. By September 28th, roughly 70% of the ship existed as separate modules stored adjacent to Building Way No. 1. The bow section, complete with anchor windlass and forward hold structure. The stern section, with rudder post and steering gear installed. 4 midship sections containing cargo holds, cross-bracing, and frames. The engine room module with the triple expansion steam engine already mounted and plumbed. The superstructure with bridge, crew quarters, and navigation equipment. This level of prefabrication wasn't standard even in Kaiser's yards. Normally, major assemblies were built progressively as the hull took shape on the ways, but the Peary project demanded that everything possible be constructed in advance so that final assembly became more like installing pre-made components rather than building from raw materials. The publicity was deliberate and calculated. Kaiser invited newsreel cameras, newspaper reporters, and Maritime Commission officials to witness the attempt. He understood that if Richmond Yard 2 could build a Liberty ship in under a week, it would prove that American industrial capacity could overwhelm any enemy through sheer production volume. The propaganda value was immense, but so was the risk. If something went wrong, if the ship failed sea trials, or if corners cut for speed resulted in defects, Kaiser would be exposed as a reckless showman rather than a manufacturing genius. September 28, 1942, 10:45 a.m. The first keel plate touched the building way. Cameras rolled as crane operators positioned the massive steel section. Welders swarmed immediately, running beads along pre-marked seams. The ceremony that traditionally took hours was compressed into minutes. By noon, the keel and bottom plate assemblies were secured. Work crews were already positioning the first frame sections before the keel welders had finished. The choreography was extraordinary. Kaiser had assigned every worker a specific task with precise timing. Team A welded keel sections, Team B positioned frames, Team C connected sideshell plates, Team D installed deck beams. Each team had its own crane, its own material staging area, and its own sequence cards that specified exactly what to do and when. Supervisors coordinated movements like orchestra conductors, ensuring teams never interfered with each other while maintaining continuous progress. By midnight, on the 28th, 12 hours after keel laying, the bottom structure and lower side shells were complete. The hull profile was visible. Welders worked under floodlights in shifts, handing torches to replacement crews without any pause in work. The noise was incredible. Hundreds of welding arcs crackling simultaneously, pneumatic tools chattering, crane engines rumbling. The shipyard ran like a precision machine, consuming steel and electricity and human labor, outputting structure at rates that seemed physically impossible. Day 2, September 29th. The midships sections lifted into position. These enormous prefabricated modules, some weighing over 100 tons, represented weeks of work done off the building way. Crane operators positioned them with astonishing precision, guided by surveyors who ensured alignment within a quarter-inch across 100-foot spans. Once positioned, welding teams connected the modules to the growing hull, using techniques Kaiser's engineers had spent months perfecting. The welding sequence was critical. Kaiser's metallurgists understood that welding created localized heating and cooling that stressed the steel. If done incorrectly, These residual stresses could weaken structures or even cause cracking. The solution was to distribute welds evenly, never allowing any section to heat excessively before adjacent areas were joined. Welders followed numbered diagrams, completing welds in specific order to balance thermal stresses across the entire hull. It was scientific welding, planned on drawing boards by engineers rather than left to the judgment of individual craftsmen. By the end of day 2, the hull was complete from keel to main deck. The cargo holds existed as enclosed spaces. Bulkheads divided the interior into watertight compartments. The basic structure that would keep the ship afloat was finished. But a hull isn't a ship. The next 2 days would install everything that made the vessel operational. Day 3, September 30th. The engine room module lowered into position. This prefabricated section contained the steam engine, reduction gears, propeller shaft, and most of the auxiliary machinery. In traditional construction, installing an engine took weeks. Workers had to fit the engine bed, align the shaft, install piping and electrical connections, test everything, make adjustments. Kaiser's pre-assembled module eliminated most of that work. The engine dropped into place as a complete unit. Workers connected steam lines, electrical cables, and control linkages using pre-planned routing that required no improvisation. Simultaneously, other teams installed the superstructure, the deck houses and bridge that would serve as crew quarters and command center. These arrived as complete modules with furniture, fixtures, wiring, and plumbing already installed. Cranes positioned them on the main deck, welders secured, mounting points, electricians connected power feeds. Within hours, the ship had taken recognizable form. Day 4, October 1st. Detail work consumed the final hours. Lifeboats mounted in davits, cargo handling gear installed, navigation equipment tested, the propeller attached to the shaft. Thousands of small tasks that each took minutes, but collectively represented the difference between a floating hulk and a functioning vessel. Kaiser had teams working every section simultaneously, checking items off master lists, ensuring nothing was forgotten. October 2nd, 4:30 a.m. Roughly 90 hours after the keel touched the building way, the SS WWII pier was ready for launch. The traditional champagne bottle broke across her bow at dawn. The restraining blocks were knocked away. The hull slid down the greased ways into San Francisco Bay as workers cheered and newsreel cameras captured the moment for posterity. But launching wasn't completion. The pier still needed final outfitting, sea trials, and inspection before the Maritime Commission would accept delivery. Kaiser's crews worked through October 2nd and into the 3rd, completing tasks that couldn't be done while the ship sat on the building way: painting, final electrical testing, loading stores and fuel, commissioning the engine and machinery. By October 3rd at 2 p.m., 4 days and 15.5 hours after keel laying, the pier sailed on her shakedown cruise, a fully operational Liberty ship built faster than anyone had imagined possible. The achievement made headlines worldwide. Allied newspapers celebrated American industrial might. German propaganda dismissed it as a publicity stunt, claiming the ship must be defective. Japanese military planners noted the construction time in intelligence reports, recognizing that American production capacity exceeded their worst estimates. The pier herself sailed successfully for years, surviving the war and proving that speed of construction hadn't compromised quality. But the record-setting 4 days obscured the more important question. If Richmond Yard 2 could build a Liberty ship in 4 days under special conditions, why did standard production still take 42 days? What prevented Kaiser from maintaining that pace for every vessel? The answer revealed both the genius and the limitations of his methods, and it pointed toward even more radical innovations that would emerge from the Liberty ship program's harsh lessons. The WWII Pier's 4-day construction impressed the public, but Kaiser's own engineers understood it was theatre rather than sustainable practice. The record attempt had consumed resources from across the entire shipyard. Those 6 fabrication shops that spent weeks pre-building Pier's sections weren't working on other vessels during that time. The specialized crews assigned to Building Way No. 1 couldn't simultaneously build ships on other ways. The concentrated effort that produced One ship in 4 days actually reduced total yard output that month because every resource had been marshalled for the publicity demonstration. More concerning was the cost in human terms. Workers logged 70 to 80-hour weeks during the pier construction. Welders worked double shifts with minimal rest. The injury rate spiked. Exhausted workers made mistakes, dropped tools, misread specifications. Several minor accidents occurred that could have been serious under slightly different circumstances. Kaiser paid premium overtime wages, which made the Peary one of the most expensive Liberty ships ever built, despite the compressed timeline. The 42-day standard represented a more realistic balance. Prefabrication reduced construction time dramatically compared to traditional methods, but maintaining quality required certain operations to proceed sequentially. Welds needed time to cool and be inspected before adjacent structure could be added. Engine installation required precise alignment that couldn't be rushed. Electrical systems had to be tested methodically to prevent short circuits or faulty connections. 42 days allowed quality control without the breakneck desperation of the Peary project. Through late 1942 and into 1943, Kaiser's yards settled into efficient routine. Richmond, Oakland, and Sausalito together produced roughly 150 Liberty ships in 1943, an astonishing output that represented nearly a third of total American Liberty ship production. The prefabrication system matured, workers became more skilled, the supply chain stabilized. By mid-1943, Kaiser's yards were launching a completed Liberty ship every day somewhere in the complex, though individual vessels still required 5 to 6 weeks from keel to launch. Then the ships started breaking. Not from torpedo damage or storm conditions, but spontaneously, catastrophically, in ways that terrified sailors and baffled naval architects. January 16, 1943. The SS Schenectady sat at dock in Portland, Oregon. She was brand new, barely 10 weeks old, fresh from Kaiser's Swan Island yard in Portland. No enemy threatened her. No storm battered her hull. The morning was calm, the water still. Then a sharp crack echoed across the harbour. Within moments, the entire vessel fractured completely in two, the hull splitting from deck to keel as if sliced by an invisible blade. Sailors scrambled as the bow and stern sections sagged in opposite directions, the ship's back broken while tied safely to the pier. The Schenectady wasn't alone. That same winter, the SS John P. Gaines broke apart in calm seas. The SS SO Manhattan, a T-2 tanker built using Kaiser's welded construction methods, cracked so severely her crew abandoned ship in panic. Between 1943 and 1944, more than 200 Liberty ships reported serious structural failures, hull cracks, deck fractures, catastrophic splits. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they couldn't send distress signals. These weren't war casualties. These were ships committing suicide. The Maritime Commission convened emergency investigations. Naval architects examined failed sections. Metallurgists tested the steel under microscopes. Inspectors crawled through hulls with measuring instruments searching for the culprit. Bad steel? Faulty welds? Design flaws? Inadequate quality control? The investigations produced disturbing findings. The steel met specifications. The welds appeared sound when examined visually. The Liberty ship design came from proven British blueprints that had produced hundreds of seaworthy ocean-class vessels. Yet, American-built Liberty ships were fracturing like porcelain teacups dropped on concrete. The cracks typically initiated at stress concentration points. Square-cornered hatch openings, gun, mount foundations, the junction between deck and hull. Once a crack started, it propagated through welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. The continuous welded structure that made Liberty ships fast to build also made them vulnerable to catastrophic failure. Riveted ships didn't suffer this problem because each riveted plate was a separate element. Cracks hitting riveted seams would stop. The mechanical fasteners created natural crack arresters. Welded ships had no such protection. The fractures showed a disturbing pattern. They occurred almost exclusively in cold water. Ships operating in the North Atlantic, where water temperatures dropped below 40 degrees Fahrenheit, suffered the highest failure rates. Vessels in the Pacific or Mediterranean remained largely intact. This temperature dependence pointed toward a phenomenon that metallurgists understood theoretically but had never seen at such catastrophic scale: brittle fracture. Steel is not a uniform material. Its properties change dramatically with temperature. Warm steel is ductile, meaning it can absorb stress by deforming slightly, bending rather than breaking. Cold steel loses that flexibility. Below a critical temperature called the transition temperature, steel becomes brittle, more like glass than the tough material welders worked with in California's mild climate. When brittle steel meets concentrated stress at a sharp corner, physics takes over with brutal efficiency. A microscopic crack initiates. In ductile steel, that crack would stop, absorbed by the material's ability to yield. In brittle steel under tension, the crack becomes a sprinting fracture. The Liberty ship design compounded the problem. British maritime architects had specified square corners for cargo hatches because they simplified construction and cargo loading. Nobody had considered that sharp internal corners create stress concentrations that multiply applied loads by factors of 3 or more. Every wave that flexed the hull sent stress spikes through those corners. When the steel was cold and brittle, those corners became crack initiation sites, waiting for the right conditions to fail catastrophically. But stress concentrations and brittle steel alone didn't explain why American Liberty ships failed, while British ocean-class vessels remained intact. The British ships used the same hatch designs, operated in the same cold waters, and were built with similar steel grades. Something about American construction methods was creating additional vulnerability. The answer lay in Kaiser's greatest innovation: speed through welding. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The investigation that finally identified the root cause began not with naval architects or metallurgists, but with quality inspectors at Kaiser's Richmond yards, who noticed a pattern in crack reports. Ships built during winter months showed higher failure rates than those built in summer. Ships constructed on certain building ways had more problems than those from other ways. And ships built during the Peary record attempt period, when welding proceeded at maximum speed, showed elevated cracking in post-delivery inspections. These observations pointed toward welding as the culprit, but not in the way Navy critics had predicted. The welds themselves weren't failing. Chemical analysis showed proper fusion and adequate strength. The problem was more subtle and more insidious. It involved residual stress, internal tensions locked permanently into the steel structure by the welding process itself. When a welder runs a torch along a seam, the localized temperature exceeds 2,500 degrees Fahrenheit. The metal expands dramatically in that heat zone. As the weld cools, it contracts, but the surrounding cold steel constrains that contraction. The result is residual tensile stress locked into the structure, unless the welding sequence and cooling pattern allow the stress to redistribute or dissipate. Traditional shipbuilding, with its slow pace and riveted construction, never accumulated dangerous levels of residual stress. Workers installed a few plates per day. Each plate cooled completely before adjacent plates were added. The riveted connections allowed slight movement that relieved stress, but Kaiser's rapid welding schedule created different conditions. Multiple welders worked simultaneously on large sections. Welds were placed continuously without adequate cooling time between passes. Large assemblies were welded while still warm from previous operations. The cumulative effect built enormous residual stresses into the structure before the ship ever touched water. The investigation focused on a specific failed vessel, the SS Manhattan. She'd cracked so severely in January 1943 that her crew abandoned her, though she remained afloat and was later towed to port. Metallurgists cut sections from her fractured hull and examined them in laboratory conditions. What they found was shocking. The steel near failed welds showed residual tensile stresses exceeding 30,000 pounds per square inch, concentrated at hatch corners and other stress points. For context, the steel's yield strength was only about 35,000 pounds per square inch. The locked-in welding stress alone was nearly enough to cause failure before any external loads from waves or cargo were applied. The truly damning evidence came from comparative testing. Investigators obtained hull sections from British Ocean-class vessels and tested them identically. The British sections showed residual stresses below 10,000 pounds per square inch, a third of the American levels. The difference wasn't in the steel or the weld quality. It was in construction sequence and pace. British yards built slower, allowing natural stress relief through time and controlled heating cycles. American yards, driven by Kaiser's production demands, locked massive stresses into structures that then failed when exposed to cold water and normal sea loads. Henry Kaiser faced the crisis that could destroy his reputation and his empire. By spring 1943, the Liberty ship program was under intense congressional scrutiny. Investigations questioned whether Kaiser's welded construction was fundamentally unsafe. Some Navy officials argued for returning to riveted construction, despite the time penalty. Maritime unions claimed that Kaiser's untrained workforce couldn't produce safe ships. Insurance companies raised rates for Liberty ship cargo. Sailors refused assignments to certain vessels known to have cracking problems. Kaiser's response demonstrated why he'd become successful. He didn't defend his methods or blame others. He acknowledged the problem and immediately funded intensive research to solve it. He brought in outside metallurgists from universities and steel companies. He gave them access to every failed ship section, every welding procedure, every construction record, and critically, he authorized experiments that would slow production if they proved necessary. The research program, based at the University of California, Berkeley, with funding from Kaiser and the Maritime Commission, ran through summer and fall of 1943. Engineers built test sections using various welding sequences and measured resulting stress patterns. They welded identical assemblies under different conditions: cold weather versus warm, fast versus slow, continuous versus intermittent. They deliberately tried to create failures in controlled conditions to understand the mechanisms. The findings revolutionized welding practice. Researchers identified specific sequence protocols that minimized residual stress. Weld from the center of sections outward, allowing stress to dissipate toward edges, rather than concentrate in the middle. Alternate welding locations to prevent heat buildup in any single area. Never complete long continuous welds without breaks. Instead, use a balanced sequence that distributed cooling stresses evenly. Allow adequate time between welding passes for cooling and stress relief. These weren't revolutionary metallurgical theories. They were practical procedures that careful welding practice should have followed all along. More importantly, the research revealed that post-weld heat treatment could eliminate most residual stress. By heating welded sections to about 1100 degrees Fahrenheit and cooling them slowly in controlled conditions, the steel's crystalline structure relaxed and internal stresses dissipated. The process, called stress relief annealing, was standard practice for pressure vessels and boilers, but hadn't been applied to ship hulls because traditional riveted construction didn't need it. Kaiser implemented the findings with characteristic decisiveness. In December 1943, he ordered modifications to all yards. Welding procedures were rewritten with detailed sequence specifications. Workers received new training emphasizing stress management over speed. Prefabrication shops installed stress relief ovens, where major assemblies could be heat-treated before final installation. Production slowed temporarily as the new procedures took effect, but quality improved dramatically. The Liberty ships built in 1944 showed markedly reduced cracking. The improved welding sequences and stress relief treatments produced vessels that could withstand North Atlantic conditions without spontaneous fracture. But Kaiser recognized that modifying existing Liberty ship production only solved immediate problems. The fundamental design had limitations that better welding couldn't overcome. The square hatch corners remained stress concentrators. The ship's low speed and archaic engine made it inefficient. The basic hull form showed its ancestry in pre-World War I design philosophy. In early 1944, Kaiser proposed a radical solution to the Maritime Commission: abandon the Liberty ship design entirely and build an improved vessel incorporating everything learned from 3 years of production and failure analysis. The Commission resisted initially. Liberty ships, despite their problems, were being produced in enormous quantities. American yards had built over 2,500 by December 1943. The tooling, the supply chains, the workforce training, everything was optimized for Liberty production. Starting over with a new design meant retooling, retraining, and accepting reduced output during the transition. Kaiser persisted with an argument the Commission couldn't ignore. Liberty ships were barely adequate. They were slow, required large crews, had limited cargo capacity for their size, and remained vulnerable to structural failure despite welding improvements. The war would continue into 1945 at minimum, possibly longer. Ships built in late 1944 would serve for years in post-war maritime trade. Why build obsolete vessels when better designs were possible? The Maritime Commission approved development of what became the Victory ship in February 1944. The design addressed every Liberty ship weakness. Rounded hatch corners eliminated stress concentrations. More powerful steam turbine engines increased speed from 11 knots to 15 knots, a 36% improvement that meant faster transatlantic crossings and reduced U-boat exposure. Larger cargo capacity improved efficiency. And critically, the hull structure incorporated crack arrestor features, intentional discontinuities where propagating fractures would stop rather than consuming the entire ship. Kaiser's engineers designed the Victory ship specifically for stress-relieved welded construction. The prefabrication, breakdown change to create modules that could be heat-treated before assembly. Welding sequences were planned on drawing boards before construction began, ensuring stress-balanced procedures rather than improvised methods. The jigs that had served Liberty production were redesigned for Victory ships with tighter tolerances and better thermal management. The first Victory ship keel was laid in February 1944 at Kaiser's Richmond Yard No. 2, the same facility that had built the Robert E. Peary 21 months earlier. Construction took significantly longer than Liberty ships. The first Victory required about 60 days from keel to launch, slower than the 42-day Liberty standard and far slower than the 4-day record. But the quality was incomparably better. Post-construction inspection revealed 0 stress cracks. The hull structure met all strength requirements with margin to spare. Sea trials demonstrated that the improved design performed as predicted. Production accelerated as workers mastered Victory ship procedures. By summer 1944, Kaiser's yards were completing Victory ships in about 45 days, competitive with Liberty timelines while producing superior vessels. The Maritime Commission shifted priorities, reducing Liberty orders and increasing Victory production. Between April 1944 and the war's end in August 1945, American yards built over 500 Victory ships. Not one suffered catastrophic structural failure. The improved welding procedures, stress relief treatment, and superior design eliminated the fracture epidemic that had plagued Liberty ships. The Victory ship program proved something fundamental about manufacturing complex machinery. Speed alone was meaningless if it produced defective products. The 4-day Liberty ship was a publicity triumph that obscured systemic problems. The 60-day Victory ship, built carefully with proper procedures, represented genuine engineering achievement. Kaiser had learned the lesson that would define post-war manufacturing philosophy. Quality and efficiency weren't opposed concepts. They were complementary when processes were properly designed and controlled. The Liberty ships that survived the war, and many did despite their problems, served in merchant service for decades. The structural issues were manageable in peacetime when ships could avoid the worst North Atlantic winter conditions and receive proper maintenance. But their wartime reputation as ships that might break in half haunted them. Sailors called them serial-numbered coffins and joked grimly about Liberty ships being cut off by the yard after being built by the mile. The Victory ships earned different respect. They were known as solid, reliable vessels that could be pushed hard without fear of catastrophic failure. The contrast illustrated Kaiser's complete manufacturing arc. He'd started by applying automobile assembly line principles to shipbuilding, achieving revolutionary speed but learning that ships weren't cars. The stresses, the materials, the operating environment all demanded different approaches. The catastrophic failures of 1943 could have destroyed him. Instead, they became learning opportunities that produced genuinely superior methods. The Victory ship represented mature understanding, where speed came from efficient processes rather than corner cutting, and quality resulted from scientific procedure rather than traditional craftsmanship. Kaiser's influence extended far beyond shipbuilding. The lessons learned in Richmond's yards transformed American manufacturing across multiple industries. The concept of prefabrication and modular assembly spread to construction, where buildings began to incorporate factory-built sections. The emphasis on welding sequence and residual stress management revolutionized pressure vessel fabrication, pipeline construction, and steel structure engineering. The quality control methods, with systematic inspection at defined points rather than final product examination, became standard practice in complex manufacturing. The welding innovations proved particularly significant. Before World War II, welding was considered a specialized trade requiring years of apprenticeship. Kaiser demonstrated that with proper procedures and fixtures, semi-skilled workers could produce high-quality welds. This democratization of welding opened the technique to mass production, while the stress relief discoveries prevented the catastrophic failures that had nearly discredited welded construction entirely. Post-war welding codes incorporated lessons from Liberty and Victory ship experience, mandating sequence procedures and heat treatment requirements that are still followed today. The shipyards themselves transformed American geography. Richmond, California was a small town of 23,000 people in 1940. By 1944, it had grown to over 100,000, the population explosion driven entirely by Kaiser's yards. The workforce was extraordinarily diverse. Women comprised about a quarter of workers, performing every job from welding to crane operation. African Americans found employment at wages and positions previously denied them in segregated industries. The yards operated as one of the most integrated workplaces in 1940s America, not from ideological commitment, but from practical necessity. Kaiser needed workers and couldn't afford to reject qualified candidates based on gender or race. This wartime integration had lasting social effects. Workers who'd proven themselves capable in demanding industrial roles weren't willing to return to pre-war restrictions. The experience of women, welders, and African American shipfitters contributed to post-war civil rights movements and changing social expectations. Kaiser's yards demonstrated that traditional barriers were artificial rather than reflecting actual capability differences. The economic impact was equally profound. Kaiser Industries, the conglomerate that emerged from wartime production, became a major post-war corporation involved in steel, aluminum, automobiles, and healthcare. Kaiser Permanente, the health maintenance organization, started as a medical program for shipyard workers and grew into one of America's largest healthcare providers. The wealth generated by wartime production funded decades of innovation and expansion. But perhaps the most significant legacy was the proof that American industrial capacity could overwhelm any opponent through systematic organization and mass production. The Liberty and Victory ship programs produced over 5,700 vessels in less than 4 years, more merchant shipping tonnage than all Axis nations combined built during the entire war. German U-boats sank over 3,000 Allied merchant vessels during the war, but American production replaced those losses and added thousands more ships. By 1944, the mathematical certainty was clear. Germany couldn't sink ships faster than America could build them. This production supremacy extended across all military equipment: tanks, aircraft, trucks, artillery, ammunition. The numbers were staggering. American factories produced more military equipment in 1944 alone than Germany and Japan produced during the entire war. Kaiser's shipyards were one component of this industrial avalanche, but they exemplified the systematic approach that made it possible, breaking complex products into manageable modules, using specialized tooling to simplify tasks, training workers for specific operations rather than general trades, maintaining quality through process control rather than craftsman skill. These principles worked for ships, tanks, aircraft, and every other weapon system. The Germans and Japanese never understood this approach. Their manufacturing remained rooted in pre-industrial craft traditions, where skilled workers produced small quantities of high-quality equipment. A German Panther tank was arguably superior to an American Sherman tank in individual combat, but Germany produced about 6,000 Panthers during the entire war. America built over 50,000 Shermans. Superior numbers overwhelmed superior quality, and the numbers came from superior manufacturing systems. Kaiser's 4-day Liberty ship was propaganda, but it was propaganda rooted in genuine capability. The ability to even attempt 4-day construction reflected organizational sophistication that Axis nations couldn't match. Japanese shipyards could build excellent warships, but they couldn't shift to merchant vessel mass production. German yards produced U-boats efficiently, but couldn't scale up to replace surface shipping losses. Only American industry had the flexibility, resources, and systematic methods to completely retool and produce unprecedented quantities of complex machinery. The Victory ship represented the maturation of this capability. It wasn't the fastest ship ever built. It was the best ship that could be built quickly in large quantities with available resources and workforce. That distinction mattered more than any single innovation. The war wasn't won by brilliant designs or revolutionary technologies. It was won by adequate designs produced in overwhelming quantities through systematic industrial organization. Henry Kaiser understood this truth better than most of his contemporaries. His pre-war construction background taught him that impressive individual projects meant nothing compared to sustained output. Boulder Dam was magnificent, but it was one dam. Victory ships were individually unremarkable, but 500 of them crossing the Atlantic simultaneously represented power that no opponent could counter. The shift from craft to system, from quality through skill to quality through process, from impressive demonstrations to sustained production, these were Kaiser's real contributions. The 4-day ship was spectacle. The 5,700 ship program was victory. The Liberty ships that broke in half during 1943 demonstrated the dangers of speed without understanding. The Victory ships that served flawlessly proved that understanding could be achieved through systematic investigation and honest assessment of failures. Kaiser's willingness to acknowledge problems, fund research, modify procedures, and even abandon established production for superior designs showed industrial leadership that transcended mere technical innovation. He created a learning organization that improved continuously, rather than defending past decisions. Modern manufacturing inherits this philosophy: continuous improvement, systematic problem-solving, willingness to halt production and fix processes, rather than continue producing defects. These concepts seem obvious now. They weren't obvious in 1943 when congressional investigators wanted scapegoats and competitors wanted Kaiser to fail. His insistence on understanding root causes, rather than applying superficial fixes, transformed not just his yards, but American industry's approach to quality management. The welding sequences developed to prevent Liberty ship cracking are still taught in welding schools. The stress relief procedures are mandated by codes for pressure vessels, pipelines, and critical structures. The prefabrication and modular assembly methods are standard in construction, manufacturing, and shipbuilding worldwide. The quality control philosophy, with process monitoring and correction rather than final inspection and rejection, became the foundation for Six Sigma, lean manufacturing, and total quality management. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.